Conjugation occurs when p orbitals can overlap on 3 or more adjacent atoms. You need to know that conjugation is important because it results in the stability of the compound. Organic compounds look for stability. If you look at these 3 compounds, they all have conjugation as a force of stabilization. You have to look at them in 2 ways. You have to first draw the resonance structures. And then, if you could sketch out the p orbitals on the molecules. So if we take a look at this right here, if you recall from organic 1, these are the curved arrows where the electrons are delocalized. You would be able to draw, there's a lone pair on the end here, there's a double bond in the middle, and then there's a positive charge at the end. If you sketch this using the p orbitals, if you recall, p orbitals are these up and down orbitals, and they actually cause the pi bonds. This is a pi bond, and of course that's a pi bond right there. So if you notice here, there's an overlap between them. This is why we say conjugated systems are more stable, because they are resonance stabilized. And of course, the density, the electron density of the pi bonds is spread over a larger volume. So this lowers the energy and stabilizes the molecule. You need electron density over a larger area to stabilize the molecule, rather than keeping it in one place. So similar to what we did first, you would like that positive charge not only on one side, but you can actually shift it. Now, again, this is just a simplistic view of resonance. Remember that resonance structures are occurring at the same time. There's a hybrid between them, but it helps us to see how we can spread electron density over a larger volume. So as you see here, this is called an allylic carbocation. The positive charge now is on the left side. Also, if you have an allylic carboanion or carbanion, you notice that there is a resonance structure where now the negative is on the end. Now, this is where it brings us to point number 3, is to delocalize non-bonded electrons or electrons in the pi bonds. There must be p orbitals that can overlap. And this means that the hybridization of an atom is different that would have been predicted using the rules outlined in chapter 1. So if you recall from organic 1, this is a minor point, but worth mentioning. If you did the hybridization, you would have thought that this was an sp3. But remember, this is a conjugated molecule, so it couldn't be an sp3, meaning if it was an sp3, then you would have no p orbital left. No p orbitals. So it turns out this is actually not an sp3 hybridized, but actually an sp2 hybridized. And the way to draw this is to draw a hybrid, resonance hybrid, where each side has a delta minus. That ensures that this is an sp2, and that side is also sp2, resulting, of course, in a structure similar to the one that we drew right here on the left. Minor point, we'll discuss this more in class. The last thing I wanted to mention about conjugated systems is that they must be planar. They must be planar to allow the overlap of adjacent p orbitals. So benzene here is planar, you can see. And you notice that you can overlap all of these p orbitals because they are parallel to each other. They are in the same plane. And we can do, of course, the ones on the bottom right there. So again, we write underneath here that planar ring allows for a continuous overlap. Of p orbitals. Versus in the second structure right here, you notice that it's not planar. It is not planar. And because of that, you cannot have an overlap, a continuous overlap between the p orbitals. So there's no overlap of p orbitals. The reason why this one looks like a tub shape is because of angle strain, if you recall that from organic 1. So again, there's no overlap here, therefore you can't actually have conjugation. Now, to bring us to the last thing we needed to mention about conjugated dienes is that you can have conjugated dienes, but not all dienes are conjugated. You can have what we call something similar to this. We have isolated dienes. If you notice here, there is no conjugation. There's no conjugation in this one. Simply because there's no p orbital right here in the middle. Versus, of course, you have a conjugated diene over here. So what's so special about this? What's special is that if you go ahead and react this with hydrogen, you would like to hydrogenate these molecules, simply like hydrogenated oils. You notice that the isolated dienes gives off more energy than the conjugated dienes. So this means, okay, so they're both the same compound, by the way, same compound. So this tells us that if we were to show this graphically, that the isolated diene started with 61 kilocal per mole, and the conjugated diene started at 54 kcal per mole, meaning that this one has less energy, started at the lower energy to begin with, meaning again, this one is more stable. So if it started with a lower energy, went down to the same molecule, 54 versus 61. So again, conjugated molecules are more stable.